Hi everyone, my name is Jeon, and today I will present our work, NetCrafter, Tailoring Network Traffic for Non-Uniform Bandwidth Multi-GPU Systems. The first author, Amel, will answer your questions via Zoom at the end of this talk. And this is a collaborative work between University of Virginia, William Mary, and King's Moncus University of Technology, North Bangkok. I'll start by briefly summarizing our work. Modern GPU systems accelerate workloads by interconnecting multiple GPUs. However, as these systems scale to meet the compute demand of emerging workloads, they typically exhibit non-uniform interconnect bandwidth. In such case, slower links often become the performance bottleneck and limiting overall scalability. To address this challenge, our goal is to optimize performance over those slower links by reducing and efficiently managing network traffic. To this end, we propose NetCrafter, a network crafting engine that stitches partially empty fleets to improve utilization, trim redundant data from network packets, and sequence network traffic to prioritize some latency-critical workloads. With this optimization, NetCrafter delivers up to 64% faster and 16% average speedup over the baseline non-uniform multi-GPU setups. This is a brief outline of today's talk. I'll start by providing some background and then motivating to our work. GPUs today are everywhere, delivering from graph processing to deep learning, VR, HPC, and genomics, and even accelerating those transformer models like GPT. However, while GPU accelerates those applications, the compute and memory capability of a single GPU cannot simply hold it. Therefore, we need to scale it. For example, GPT-3 alone demands thousands of gigabytes of memory and petaflop days of training. And clearly, a single GPU can no longer meet these demands, highlighting the limitation of standalone single GPU solutions. That's where multi-GPU comes to the rescue. By connecting multiple GPUs over high-speed interconnects, this system overcomes the limitation of a single GPU by scaling first compute, by harnessing collective compute power of multiple GPUs, and also scale memory by pooling memory across GPUs for a larger memory space. This is exactly what commercial systems are doing, like NVIDIA and AMD. However, multi-GPU system must continue to scale with growing demands of modern applications. As we scale beyond a single GPU cluster, it typically adopts a hierarchy interconnect design with fast, high bandwidth links connecting nearby GPUs and slower links connected far GPUs. This hierarchy introduces non-uniform bandwidth across all GPUs, creating new bottlenecks as the system scales. Now, let's look at the repercussion of this non-uniform bandwidth on our multi-GPU system. Non-uniform bandwidth across GPU links creates a NUMA-style system where remote access costs far more than local ones. To understand how this works, let's take a closer look of traditional single GPU memory access paths. There is SAMD wavefront will issue fine-grained load and store, and there is a classing unit to merge access into 64-byte cache line request. This flow are later forward to L1 TLB and L1 cache, and then this goes to the GMMU and the shared L2 cache, which is backed by the high bandwidth memory. Finally, any access that is missed or targets remote memory is handled by the RDMA engine for a peer GPU fetch. Nearby GPUs enjoy higher bandwidth and lower latency, and far GPUs experience low bandwidth and higher latency. To quantify the impact of non-uniform bandwidth on application performance, this figure shows the performance across different multi-GPU setups. Some GPUs are connected via slower links, which is the reality case, and we consider an ideal case that all GPUs are connected using high-speed links. And you can see slower links introduce significant slowdown with, for example, image to column suffering up to 2.3 times drop in performance. This clearly motivates smarter traffic crafting across slower links. This brings us to the key challenge of this work. Slower interconnects lead to performance bottlenecks. Then, how can we minimize the impact of such non-uniformity in such emerging new multi-GPU systems? To address this challenge, our goal is straightforward. We need to optimize slower bandwidth links by reducing network traffics across those links and by efficiently managing network traffics. To achieve this goal, we make a few observations and propose our three main key ideas. Before we dive into our observation, let's see how GPUs send data over network. Network transfer happens in the granularity of fleet, which is the basic unit sent across the network. Each GPU request becomes a packet, which is composed of a header, which contains the metadata to route the request over the link, and the payload, which is the actual data that needs to be sent over the link. The packet is then split into multiple fleets being transmitted to the network. If the packet size is not a multiple of the fleet size, the fleet is padded with empty bytes to align to the fleet size. And then finally, the fleets are sent across the network. Now let's discuss our first observation, which is inefficient fleet utilization due to padding. As we discussed, fleet contain empty bytes, which are then padded with redundant data. The redundant data increase unnecessary network load. We further observe that there are different packet types in such network links. Those packets have different sizes and therefore different padding granularities. If you look at the breakdown by packet type, you'll see that read request and page table response send mostly header fleets, while write request and read response fare slightly better, but still pad their lost fleet. We see each packet type pad a different fraction of its lost fleet as shown below. We further evaluated different workloads to say the percentage of fleets which had redundant bytes padded to them, as shown by this figure. Overall, we observed that around nearly 40% of all fleets in the network are padded with either 25% or 75% redundant data. This brings us to our first key idea, which is stitching. We propose to intelligently stitch fleets across request categories to reduce the total network traffic. This figure depicts a few network packets traversing the network. For better understanding, let's do a walkthrough of our stitching approach, assuming those packets traversing the slow links. You can stitch fleets from the same package. For example, you can stitch between read response. You can also stitch write response fleet to its payload and with the preceding page table request to get rid of one more fleet in the network. Here, page table response fleet can stitch its payload data with a write response fleet. Again, write response fleet can stitch its fleet data with a read response fleet. And finally, the read request fleet stitches its fleet data with a write response fleet together. All in all, we are able to get rid of a total of 5 fleets from the network. And this helps to reduce the total network traffic over the slower network link and to improve bandwidth utilization. Details on the decision of the stitching logic and fleets and the packet structure to support stitching can be found in the paper. Now let's move to our second observation, which is prefetch unused data waste bandwidth. As discussed previously, access generated for the same cache line by a wavefront are collapsed by the collector and issued as a single cache line request. We observed that read response may include more data than requested, which wasted the network bandwidth. Digging into traffic, we found that most applications only require 16 bytes or less from a 64-byte cache line. But however, GPUs still fetch and shape the full 64 bytes over the network. This gives us our second key idea, trim. Trim away unneeded bytes so only the requested data travels over the slower interconnect. An example is shown below. When the remote GPU hosting the cache line is ready to satisfy the packet request, we analyze it to determine the exact number of bytes requested by the wavefront. If the number is 16 bytes or fewer, and the response packet had to traverse across the slower links, we then cut those unneeded data. Otherwise, we don't perform trimming to maintain spatial locality. Our trimming approach further helps to reduce the network traffic. And our third observation shows that page table worker traffic is more sensitive to latency than just regular data access. We run 2 experiments under non-uniform links. One, we prioritize page table worker related fleets, which is shown in the green bar, and one is we prioritize data fleets, which is shown in the blue bar. In almost every benchmark, giving the page table worker fleets to LED yields higher speedup. This tells us to reduce stall and page fault penalties, we should sequence page table worker related packets ahead of regular data on slower links. Based on this observation, we propose our final key idea, which is sequencing. We propose to prioritize fleets in flight, so latency critical packets lead the line on the slower links. This will help to reduce the execution time. Putting it together, NetCrafter's stitching, trimming, and sequencing works to slash unneeded fleets, eliminate wasted data, and accelerate critical traffic on the slower link, which satisfies our goal. Now we'll dig deeper into the NetCrafter design details. Our NetCrafter controller contains our stitching, trimming, and sequencing engine, and is integrated within each cluster switch. The packet will first come into the switch. We first check whether the trim signal is enabled. If yes, we then trim the packet and send it to the next stage for stitching. The stitching logic contains a cluster queue or CQ structure, which is partitioned by two levels, first per destination and then per type. Packets will be in-queued and then wait for selection. We then run stitch candidate search to find two candidates to be stitched. More details of this algorithm can be found in the paper. And once the candidate is there, we will inject a small header, if required, into the fleet to support correct unstitching at the target. The stitched fleets are then ready to be shipped and sent back to the multiplexer for another chance of stitching. To further optimize stitching, we also designed a fleet pooling process to allow more opportunities for stitching. Please check the paper for more details. Now, we will talk about our setup and evaluation. We use mGPU sim to implement NetCrafter. We simulate a 4 GPU setup. Detailed configuration are shown below. We also evaluate on 3 design point, which is the baseline, where we use non-uniform bandwidth connection, and also a sector cache baseline. And then it's NetCrafter with our proposed mechanisms. Here are our results. NetCrafter with all 3 mechanisms provides 16% speed up on average, with a maximum speed up of 1.64 times. And we evaluate different combinations of our mechanism. For example, stitching plus trimming could reduce network traffic, while sequencing can efficiently managing network traffic. Lastly, we compare our design toward a sector cache design, where the remote cache line request is also sectored. This is to show the effectiveness of our trimming mechanism. And it is clear that our trimming mechanism outperformed this sector cache baseline. Before concluding, I would like to highlight that there are a few more details covered in our paper, but omitted here due to time constraints, such as fleet pooling, select fleet pooling, which enhance the stitching efficiency. There is also package structure modification associated with overhead and other implementation details. Please check the paper for more details. And with this, I would like to conclude. We focus on the problem of multi-GPU non-uniform interconnects. To this end, we propose NetCrafter, a combination of novel approaches, stitching, trimming, and sequence, to deal with multi-GPU network traffic, which provides up to 64% speed up and 16% speed up on average. Our proposed techniques are generic and can be applied to any other traffic. They are especially useful in alleviating the bottleneck presented by lower bandwidth network connecting multiple groups of GPUs. And thanks, and questions are welcomed.